We will begin to show our processor and explain the important parts of it, including the program counter or 32-bit register and control unit, ALU, and the display driver. So, because the RAM and ROM register are all provided on Moodle, and we won't talk about it here, and they will all be included in the explanation of function later. Alright, reset it. Open it again. Reset it. Okay. Let's begin with the program counter. Program counter of PC is actually a 32-bit register, which is made up of 32 resettable D flip-flop, and this is the structure of the resettable D flip-flop. Each time to run a new program, PC or program counter will be initialized to 0, and for each time have new instruction, it will increase by 4 bytes. With this to 32-bit adder, 4 bytes is added to the new is added each time, unless some special function like jump or branch. Then we comes to the control unit. The control unit is composed of two parts. One is a main decoder and another is a ALU decoder. The main decoder directs operation of the other units. And for the main decoder, it takes in 6-bit code from the OP520, which are the most significant instruction space, which is 31 to 26. Then we can get the output here, which can either be 1 or 0. The output tells the processor how to respond to the instruction, like in a jump or branch or write. And the main decoder is made up of combination logic gates here, which can be created by study the K-map of main decoder. Another part of the control unit is the ALU decoder, which here. And the ALU decoder has two inputs. One is from the main decoder ALU OP120, and another is a function 520. So according to the ALU decoder's K-map, if the OP1 equals to 0, then the function input can actually be ignored. So inside the ALU decoder, we set two constant value, which is 110 and 010. One for the addition and another is for the subtraction, to maintain these two functions still works. And the block here, which I call it the ALU decoder multiplexer, it will combine all the inputs of the ALU decoder, about 10 here, and transfer it to the 3-bit output of the ALU decoder, which will feed to the ALU later. The third circuit I would like to explain is the ALU, also known as arithmetic logic unit, respond to the logical operations inside the whole processor. It has 3 inputs. One is from the control unit, the ALU control to 0, and one is from the register, and another one is from the sign extent. And it has 2 output. One is the ALU output 31 to 0, which will feed to the display driver and the data memory, and another is 0 output. So inside the ALU is basically just a 32-bit adder and a 32-bit subtractor and a 4 to 2 multiplexer. It can do the function include add, sub, set less than, and OR. The last part I'm going to explain is a display driver. For this display driver, we have 6 outputs, which are corresponding to the 6 digits on our FPGA. And the performance of the display driver depends on the address, the data address on the bus A. If the bus A address is equal to the 7F and 0, or you are equal to the 7F and 1, it will show different results. And we can use a comparator to check which value it's equal to. So if the value on bus A is equal to 7F and 0, then the 6 digits will display the number which processed by the RAM, ROM, and register. And if the address is 7F and 1, the 0 will be stored. The 0 bit will be stored in the flip-flop, and the output of the flip-flop will decide whether the 6 digits are blank. So the whole design, the design of the display driver can be divided into 2 parts. One part is this part, about bus part, is to have normal display, and this part will show blank. And we also have a reset line here. If the reset is high, then the display should all reset to 0. It means the 6 digits will all show 0. At the same time, the register and the single flip-flop here will also be resetted.
Hello, my name is Xinsu, and I'm going to explain how some of the functions works on the processor. When the reset input of the program counter is activated, it supplies the address to the RAM, and RAM takes the value of the instruction at that address on bus as the output. The instruction has 32 bits in total. The 31st bit and the 26th bit is the opcode. It defines which function will be activated. And the 25th bit to the 21st bit is RS. The 20th and to the 2016th bit is RT. And the last 16 digits is INM. We will set opcode as 000100 here, which the branch function will be activated. And the RA1 and RA2 input of the register file is RS and RT respectively. There are 2 outputs of register file, which is RD1 and RD2. RD1 will go to the ALU directly, but the RD2 must go through a multiplexer here, because when the function is load word and save word, the sign stand which load the value of INM must go to the ALU, but in this case the RD2 must go to ALU. So the multiplexer is used here, which the switch is depend on the opcode, and the opcode and the ALU source here is 0. So the RD2 is go to the ALU as input. In this case, it is the branch function. So the ALU control code is 110, which subtract instruction will be execute. If the 2 input is equal, the Cout, which is the 0 out, will output 0 to an AND gate, because the branch is 1 here. So the output of the AND gate really depends on the output of Cout. If the Cout is 0, the PC source is 0 here, and if the Cout is 1, the PC source is 1 here. and the PC source code is connected to another multiplexer here. This multiplexer is used because PC takes not just one address. One input of this multiplexer is connected to PC plus 4, and the other is connected to an adder. This adder add together the sign extend, which is the INM times 4, and PC plus 4 here. So this is PC plus 4, this is PC plus 4 plus 4 times the value of INM. And when the output is PC plus 4, the PC is set to the next instruction. And when the when the output is PC plus 4 times the INM, the PC is branch target address.
This is the code for square program, and it displays the square of number from 0, so it should display 0, 1, 4, 9 each time. And for this one, for the first line is stored the first value, starting value should be 0, and the second line means that it sets the value of the difference of two successive numbers. Because in this program, for example, the value starts from 0 and 1, 4, 9. The difference between them is 1, 3, and 5. So it increased by 2 each time. As a result, in the loop part, we just need to add the difference to each time. Then in the final display, it will show the 6 digits will show the proper number.